Welcome back into our lecture series regarding static fluids. Last time we saw how to basically calculate density of solids, liquid, and gases, and how to actually create the pressure exerted by them. And we also said that fluids, we defined it as anything that has fluid motion, and that could be either air or it could be liquid. So today we're going to look at atmospheric pressure. So how does atmospheric pressure basically get generated? So imagine we have a table, and we have a number of particles that exerts from the surface of that table all the way up to the upper troposphere. The weight of all those gas particles, it exerts a weight and a force on that table, and that's what basically atmospheric pressure is. Atmospheric pressure is of course measured in pascals, as we said last time, because that's newtons per meter squared, and the value is 1.0 times 10 to the fifth. That is one of those quantities that you absolutely have to remember, along with the density of water. Density of water is, once again, 1 times 10 to the third, and atmospheric pressure is 1 times 10 to the fifth. They're just off by 2 orders of magnitude in relation to pressure and density. So, please, from now on, I need you guys to remember that atmospheric pressure is 1 times 10 to the fifth. So, now we're going to look at the relationship between pressure and depth of any kind of fluid, and in this case it's going to be static fluid. So imagine we have a standing body of water, and we have a column in that body of water. So imagine we take that column out, and now let's draw a free body diagram. So we're going to have a force at the bottom of that column of water and a force on top. Now, any diver will tell you that the force at the bottom is always going to be a lot greater because they can simply feel the pressure. The deeper you go, the more pressure you are going to feel. So force at the bottom of the column is always going to be a lot greater than the force on top. So if we are to set up an equation, we would see that the force at the bottom is equal to the force on top plus the weight, because that's the force of gravity, so the weight of the water of the molecules above it. You can see this by this equation right here. So once again, the force at the bottom is equal to the force on top plus m times g, the weight really of the molecules of the water, and that's the force of gravity. So now, since the force we saw last time is equal to pressure times area on top, plus m times g, we can rewrite the equation just like this. And now mass is equal to what? It's equal to, we saw this, the volume times rho, the density rho. So when we plug all things in, it becomes this format. So rho density equals volume times g, the acceleration due to gravity. And volume now is what? It's area, because it's length times width times height, and that's what volume is. So we can put area times height in terms of that, and we divide every part by area, so it becomes pressure at 2, meaning at the bottom, equals pressure at 1 on top, plus rho g h. And this is the equation I need you to know. Now, I went through the derivation, but you don't really need to know it. It's good to know where things come from, but this is the equation where you need to know and you need to manipulate. Once again, pressure at 2 at the bottom is equal to pressure at 1 plus rho times h times g. So now, let's solve our first problem. Okay? So we have points A and B, as you can see over here at the bottom, located at a distance of 5.50 meters beneath the surface of the water. And we have to find the pressure at each of these 2 points. Note please that A and B are both the same distance below the surface of the water. So now, let's go into our sketch pad. Let's open this up. And let's see, what was our formula again? Because now we're talking about static fluid, so therefore we're talking about pressure created by depth of a fluid. So that is going to be, of course, pressure 2 equals pressure 1 plus rho g h. Okay, this equation, I don't mind if you memorize it or not. It's going to be given to you. It's going to be in your reference tables. So now, we're trying to calculate the pressure at point 2. Now I'm just going to draw a brief little diagram right here. This is point A, that's pressure 2. So point A is really pressure 2. We have a rock in the middle, and here is point B, and of course it is really the same distance from the surface of the water, and that's going to be 5.5. Okay, so we're trying to find this over here, the pressure at point A, so that's going to be P2. Now, what is pressure 1? Remember, we have a column of air that extends from the surface of this water all the way up to the troposphere. So what is that? That is atmospheric pressure. So that is 1 times 10 to the 5th pascals. And now we're going to add rho times g times h. Rho, of course, is density, which is what's the density of water? 1 times 10 to the 3rd. G, of course, is 9.8 meters per second squared. And going back over here, it's going to be kilograms per meter cubed. And, of course, the height is going to be 5.50 meters. So now, when we multiply these three quantities, 1 times 10 to the 3rd times 9.8 times 5.5, which is the height, and we add it to 1 times 10 to the 5th pascals, we see that it's going to be 1.55 times 10 to the 5th pascals. So that's the pressure at A. Now, what's going to be the pressure now at B? Well, guess what? It's going to be exactly the same thing. Because why? It is still the same distance of 5.5 meters from the surface of the Earth. Make sense? So, going back to our presentation, we see that moving on, we see, here we go. Again, pressure 2 is pressure 1 plus rho GH. Of course, pressure 1, 1.1 times 10 to the 5th. Rho is the density of water, g, acceleration due to gravity, and height is 5.5 meters in depth for a total of 1.55 times 10 to the 5th pascals. So now, let's do one more problem. Let's calculate the difference in blood pressure between the feet and the brain of a person with a height of 1.35 meters. Again, let's go back to our sketch pad right here. Let's clear everything up. And our formula, of course, is going to be the same. Because why? We're talking about the pressure that is generated from the depth of a fluid. So, what is it? It's going to be P2 equals P1 plus rho times G times H. And the only information that they give us, the height of the person, which is 1.35 meters. Now, notice what the problem said. The problem asked, what is the difference in pressure? So what's really the difference? So you bring pressure over here on this side, so you subtract pressure 1 on either side, and it becomes pressure 2 minus pressure 1. That's the difference in pressure equals now rho, density times g, acceleration due to gravity, times h. So now it becomes very easy. So rho, again, density of blood, that, if you recall correctly, that's 1,060 times g, acceleration due to gravity, which is going to be 9.8 meters per second squared, and of course the height, and that's going to be 1.35. And if we take and multiply all three quantities together, that of course is going to be, we're going to find that the difference between the pressure of blood between the feet and the head, the cerebrum of a person, that is going to be 1.4 times 10 to the 4th pascals. Okay? Please do it and make sure you come up with exactly the same answer. Thank you so much, and we're going to practice this a lot more in class tomorrow. Thank you so much. Bye.